We are on. We are on.
All right. Welcome, everybody. Good morning, good afternoon, and good evening to one and all present here from different cities and countries. This is Deepti this side from Breakthrough Science Society. Breakthrough Science Society is an all India science organization constituting a group of scientists, research scholars, IT professionals, lecturers, teachers, and students involved in inculcating and promoting scientific outlook and logical faculty of mind to establish a scientific culture in society. We have been actively working in various institutions and different localities to popularize science, its advancements, along with effectively communicating science and its relation to society. With chapters actively present across 20 states, I'm sure we all know we are all living in COVID times, but we haven't stopped our activities. We wish to show you certain publications that we have come out with in recent times, and these are all available on the Amazon. So here you go, you see a couple of publications: The Brief History of Science, Seminal Thoughts, Science in Ancient India, Integrating Science with Society, Why We Need a New Science Movement, a couple of publications in Tamil, Bengali, Hindi, Gujarati, Malayalam, and many more of our quarterly journals that we have brought it up on regular basis. So that's breakthrough for all of you. Having said no more, I have the honor to present you Professor Jasjeet Singh Bagla, who would speak on the occasion today. Today's webinar is of prime significance. A webinar on Nobel Prize in Physics 2020 on black holes and singularities. I'm sure all of you are excited to hear out from Professor Bagla. I now request Dr. Rashmi, Associate Professor, Department of Earth and Space Sciences, Indian Institute of Space Science and Technology, Trivandrum, to introduce Professor Bagla. Over to you, Rashmi.
Thank you, Deepti. Our speaker today is Professor Jasjeet Singh Bagla from Indian Institute of Science Education and Research, Mohali, who will talk to us about this year's Nobel Prize in Physics, awarded to Roger Penrose, Andrea Ghez, and Reinhard Genzel for theoretical and observational understanding of black holes in our universe. Professor Bagla's research and teaching has brought him close to the work of all three Nobel laureates. His research interests are in astrophysics, gravitation and cosmology, particularly focusing on cosmological and body simulations and gravitational clustering. His group was the first doing in-body simulations in India. He uses both theoretical and observational tools to address structure formation in the universe. Before joining IISER Mohali, Professor Bagla worked at several institutions in India and abroad, such as the Institute of Astronomy, Cambridge, Harvard Smithsonian Center for Astrophysics, and the Harishchandra Research Institute in Allahabad. Jasjeet is an excellent teacher. He has a long career teaching various physics courses to undergraduate students. He also holds an active interest in science education and popularization. We're extremely happy to have you with us, Jasjeet. Over to you.
Thank you. Thank you, Reshmi, and thank you, Deepti, for the kind introduction. Shall I share my screen now?
Sure.
Yes, sir.
Excuse me, something seems to have happened.
Any problem with sharing?
Yeah, so I'll get started. No, my open office window had suddenly disappeared. I had to just restart it. So thank you, everyone. I'll now get started. I'll be speaking about Nobel Prize in Physics 2020, and this has been shared between Roger Penrose, who gets half the share, Reinhard Genzel, and Andrea Ghez. They get 1/4 share each. The Nobel Prize in Physics 2020 was divided in this way. Roger Penrose got his share for the discovery that black hole formation is a robust prediction of the general theory of relativity, and the other half jointly to Reinhard Genzel and Andrea Ghez for the discovery of a supermassive compact object at the center of our own galaxy. These are two very distinct works, even though there is a common theme of black holes between them. The Roger Penrose part is mostly theoretical, whereas for Reinhard Genzel and Andrea Ghez, it required a lot of technological effort in order to observe what they have observed. So the talk will essentially be in two parts. I will try to bridge them somehow because the progression of ideas essentially is going smoothly one to the other, but they are influencing each other, but the areas are quite different. Roger Penrose, Sir Roger Penrose, he's emeritus professor of mathematics at the University of Oxford. He was born in Essex in England, and he trained as a mathematician. He graduated from University College London and went on to do his PhD from Cambridge on tensor methods in algebraic geometry with John Todd. And he introduced use of topology of light cones to study spacetimes. That is the key work which got him the Nobel Prize. He has worked on a lot of other things, and I will briefly mention them at some stage. So the story, of course, for anything related with gravity pretty much begins with Newton. And Newton conceptualized gravitation as a universal force in the 17th century. And his formulation was successful in explaining planetary motions as well as terrestrial phenomena. Gradually, scientists started to analyze implications of gravitational force. And of course, you look for implications rather than just verification once you have seen it at work and seen it at work successfully. Discovery of Neptune in 1846, as predicted based on observations of Uranus. Perturbations of Uranus's orbit from what was expected was amongst the was a high point amongst many successes of Newtonian theory of gravity. So this is one input. Another essential input is the knowledge of that light has a finite speed. Romer, the Danish astronomer, he was the first person to measure the speed of light. And he did so by observing eclipses of Io, a satellite of Jupiter. And he found that the time period appeared different depending on whether the Earth was approaching Jupiter or whether it was going away. So it's good old Doppler shift. And he used that to estimate the speed of light. And clearly, I mean, he got the correct order of magnitude, not the correct number. But even that was scary enough because it was much larger than any other speed that humans had encountered. You might wonder why he was trying to do careful timing of eclipses of Io and other satellites of Jupiter. Well, there was a challenge open at that time in the 17th century on devising a time-keeping device which would work even at sea. And he thought that if we used something other than the sun or the moon, then maybe one will be able to get something interesting out. And he did discover something interesting, but not directly related to timekeeping at that time. So with these two inputs, the large speed of light and the universal force of gravitation, the ground was ready in some sense for interesting speculation. And two people took it up independently, John Michell and Laplace. Both of them essentially asked the question that, look, sun shines very brightly. We have some idea of how massive it is. We also have an idea of how large the sun is. Could it be that we have a star, or we have stars like the sun, except they are much bigger, so that their gravity is so strong that light cannot escape. So both of them essentially use the escape velocity formula in order to uh, both of them use the escape velocity formula in order to come up with an expression for the mass and radius of objects, which will be what they called as dark stars. So this is the first effort towards thinking of extreme gravity and what would later on come to be known as black holes. There is a critical difference, of course. When we use the escape velocity formula, all we are saying is that light cannot escape to infinity, but it can be seen by any observer at a finite distance from such a star. So fast forward to Einstein, and Einstein formulated his theory of gravity, the general theory of relativity, and he proposed that gravity should not be treated as a force. Instead, he said that gravitational effect modifies space-time in the vicinity of objects, and other objects move in this curved space-time. Einstein's theory tells us how space-time gets modified and also how particles moved in a curved space-time. The mathematics which he used was based on what had been developed much earlier by Gauss and Riemann. And he also showed that although global inertial frames of Newton and special relativity are no longer valid, if we have a freely falling object, then any frame tied to that freely falling object can use special relativity in small region in the vicinity. So one very interesting feature over here is that earlier the global inertial frames of Newton and Einstein himself in special relativity had to be inertial. There had to be no acceleration. And now we are saying that any freely falling frame is locally inertial frame. Einstein gave his theory of relativity in 1915, and very soon Karl Schwarzschild came up with the first exact solution. And his solution was for point mass. And of course, in that case, spherical symmetry and time independence is assumed. And because it is a point mass, the solution is clearly singular. And what was more interesting was that singularity at the origin is surrounded by a horizon such that nothing from within that can escape. Now, this was very different from what had been conceptualized as dark stars by Mitchell and Laplace, where light could not escape to infinity. Over here, what is being said is that there is a horizon with a finite radius and nothing can escape from that horizon. If something is outside, light or matter from there can go anywhere. But if anything is inside the horizon, no light, no matter from there can escape to outside the horizon. So in that sense, it's a one-way membrane. So this is a nice graphic from hyperphysics. So the black circle at the inside is that marks the horizon, event horizon for the Schwarzschild black hole. So if we have something which has the mass of 3 times the mass of Sun, the radius of this is 9 kilometers. For Sun, the radius is 3 kilometers, essentially saying that the radius of the event horizon is proportional to the mass of the black hole. If you took Earth, then the radius would be 9 millimeters. So one will have to take Earth, compress it to within 9 millimeters in order to convert it into a black hole. Another interesting scale which is marked over here is the so-called photon sphere, which is at 3 by 2 times or 1.5 times the event horizon radius. So what this corresponds to is the radius at which photons can be in a circular orbit around the black hole. It's an unstable circular orbit, but it exists, and the existence of this photon sphere is a critical thing which was used by the Event Horizon team to do the imaging of black holes or imaging of the event horizon last year. So a summary: which is that event horizon is at 2 gm by c square, c being the speed of light, g being the Newton's constant of gravitation, and m being the mass. Nothing can escape from the event horizon. Things can fall in. Therefore, this is a one-way membrane. Photons can be in a circular orbit at a radius of 3 gm by c square. This is what was marked as photon sphere in the figure on last page, last slide. And the smallest stable circular orbit for massive particles is at a radius of 6 gm by c square. So twice that of photon sphere. Nothing can be in a stable orbit inside 6 gm by c square. And one other point which I will not elaborate on, but mention over here, is that unlike Newtonian mechanics, where if a particle has non-zero angular momentum, it can never fall to the center. Over here, in case of relativistic mechanics, the centrifugal barrier does not extend to infinite energy, and particles with a finite non-zero angular momentum can also fall to the center if they have high enough energy. Carl Schwarzschild in that year, in 1916, also found the solution for space-time for a star, which is not a point mass, which is an extended mass distribution. He assumed spherical symmetry, and for a star like the Sun, the solution is not singular. The solution outside of the star matches with the solution for a point mass with the same mass as the star, but the interior solution depends on the details of density, pressure, and how these vary with distance from the center. So what is shown on the right-hand side is a graphic representation of how the space is curved. Time is not very relevant over here for the simple reason that these are both static space-times. There is no variation with time taken into account. The lower one is for a point mass, and one can see that there is a singularity or something strange happening at a finite circle. That circle actually marks the event horizon. There is no singularity there. Singularity is sitting at r equal to 0. Whereas for space-time for a star, there is no such abrupt transition at an event horizon. There is no event horizon in this particular case. And the space curvature, in some sense, smoothly varies near the center. Schwarzschild unfortunately died very shortly after he gave these solutions. He had been at the war front in Russia, and he contracted an autoimmune disease. It happens to be a disease that one particular set of Jews are susceptible to, and he died very shortly after publishing these papers. So there was no progress on his side. The same solution in different formulation was rediscovered by a couple of other people, and it took a while before people could show that all of them were essentially talking about the same solution for a point mass or for a star. Now, so it remained till Chandrasekhar came along in 1930s, and he pointed out that white dwarf stars cannot have a mass more than 1.4 times the mass of the sun and be stable. So this limit which he derived, now it is named after him, called the Chandrasekhar limit. It was derived by combining special relativity and quantum statistics. So what Chandrasekhar did was to ask that if I have Fermi-Dirac particles which satisfy the Pauli exclusion principle, which means no two of them can be in the same state, compressed to very, very high densities, then they essentially repel each other because two of them cannot be in the same state, in the same place. So there is a Pauli repulsion, so to speak. What is the effect of that pressure on the structure of white dwarf stars? In white dwarf stars, the electrons coming out of helium atoms, because the whole thing has been compressed so much, provide what is also called the degeneracy pressure. Special relativity comes in because the energy of these electrons is very high, and the energy momentum relation from non-relativistic mechanics is no longer applicable, and a relativistic expression has to be used. So Chandrasekhar did use that, and he found that it is not possible to have white dwarf stars with a mass greater than 1.4 times the mass of the sun. What are white dwarf stars? These are compact and highly dense endpoints of evolution for stars like the sun. And nobody knew of any other kind of a stellar evolution endpoint. So most people believe that stars end up as white dwarfs. All stars end up as white dwarfs. But with the Chandrasekhar limit pointed out, it was clear that one has to worry about what happens if a white dwarf of a larger than the Chandrasekhar mass limit mass forms, or if there is a white dwarf and you throw something into it and its mass becomes larger than 1.4 times the mass of the sun. A little bit later, neutron stars were conjectured, but these, because they were discovered much, much later, people did not think so much about them as natural endpoints of stellar evolution. So, next question is, what if there is a star and it begins to implode? That question was answered separately by two groups. One was by Vishweshwar Dutt from Presidency College. He discovered the analytical solution for collapse of a pressureless spherical ball of dust. Unfortunately, he died shortly after that in a surgery in 1938. His solution was dug up later, and it was finally published in a journal, Journal Relativity and Gravitation, in 1997. Oppenheimer and Schneider independently discovered the same solution in 1939, and they showed that this leads to formation of an event horizon and a black hole. So you can start with a finite-sized object which has a space-time which is not singular, so space-time which looks like the top figure over here. And because of collapse of matter towards the center, what Oppenheimer and Schneider and of course Vishweshwar Dutt pointed out was that it leads to formation of an event horizon and a black hole. So there was some criticism of the work in the sense that they had ignored pressure and they had taken a spherically symmetric object. They had not worried about rotation. Most stars seem to have rotation. They had not worried about pressure. Most stars have gas pressure. And therefore, people wondered whether it will actually be applicable to real stars or not. So it remained for a long time until much, much later. And the next trigger for serious thinking in this direction came in 1960s. So we are talking about almost 25 years after Vishweshwar Dutt's calculation and 24 years after Oppenheimer and Schneider. Martin Schmidt, he was an observer working from Caltech. He found the redshift of an optical star-like object, which he thought was associated with the radio source 3C273. And he found the redshift to be 0.158. So 3C273 number refers to the third Cambridge catalogue of radio sources, and 273 means that it was the 273rd object in that particular catalogue. The positions that had been determined through radio observations were very poor. So Martin Schmidt had to make use of other observations to improve the idea of direction where this thing could be. And what he found was that there was a star, very faint star, but not terribly faint. Those of you who are into amateur astronomy will appreciate that it is 13th magnitude, which means 7 magnitudes fainter than what we can see with our naked eyes. He found the redshift to be 0.158, and this was the largest redshift known at that time by a very wide margin. So much so that he had to struggle for a long time to make identification of lines, because mentally he was not tuned to thinking of even possibility of such large redshifts. So at the bottom, I have reproduced the top part of his paper from Nature. The paper is just over half a page in Nature, and it was accompanied by another paper where they had done an analysis of spectra for other 3C sources. Now, because the object is so far away, if the redshift was indeed cosmological in origin, and it was fairly bright. The only viable explanation for the source is that there is some matter sinking towards a black hole. And theorists around that time, like Donald Lynden Bell from Cambridge, he argued that matter forms a disk around a black hole, and matter heats up to very, very high temperature, and that is what gives rise to very bright emission over here. So the reason why a black hole is required is that a black hole is very, very compact, and therefore a falling object of any matter which is sinking in towards the black hole can go very, very deep into the potential well, and the original potential energy gets converted to thermal energy via kinetic energy. How does that happen? Well, if you form a disk around a black hole and it is a continuous disk, then the segment of the disk at each radius is has its own rotational time period and its own rotational velocity, and adjacent rings, so to speak, have a slightly different velocity, and viscosity gives rise to friction and heating, which is why the matter in the accretion disk heats up. So this was the thinking at the time. There had been a kind of wrong track taken up in between when Lifshitz and Kalatnikov showed that the Oppenheimer and Schneider calculation, when generalized to things with pressure and departures from spherical symmetry, does not lead to formation of a singularity. Of course, it turned out to be wrong, but that's something for later. So what exactly does an event horizon do, and how does it trap things inside? So this is something which can be illustrated using what are called tortoise coordinates. And these were mathematically written down by Roger Penrose, although he credits Eddington and Finkelstein with the idea. It could be Eddington and Finkelstein had certainly written about asymmetry of light cones and null cones, but they had not written down this coordinate system. It is possible that privately they communicated the idea to Penrose, who gave it mathematical shape. The name Eddington-Finkelstein coordinates stuck once Misner, Thorne, and Wheeler wrote their book on gravitation, and they used this particular name. Anyhow, so what is seen in these coordinates is that when something is very far away from the event horizon, in that case, the light cones are distorted, but distorted very little, like this one over here. So as you are aware, if the observer is at the point in the middle of this cone, the downward portion refers to the past light cone, which means the observer can see anything from these regions. So things which are far away can be seen from earlier times and so on. And the upper part of the cone is the future part of the light cone. And so light can travel along this cone, any direction along this cone, starting from this point. If you have a massive particle, that must remain within the light cone. You can see that there is a slight asymmetry in the sense that the angle of the light cone, part of the light cone towards the black hole or event horizon, which is on the left corner, left edge, is slightly steeper than one on the right. If there was no gravity, both these angles would be 45 degrees. Now, as we go further towards the event horizon, we can see that the asymmetry becomes sharper. You look at this fellow, which is just outside the event horizon at 2 gm by c square. Over here, you can see that the outgoing light cone can barely escape over here. So if I were to draw the figure for a light cone at the event horizon, it will turn out that the outgoing light cone would be parallel to, would correspond to r equal to constant, and the inward light cone would point towards r equal to 0. So once any massive particle crosses this event horizon, all forward trajectories take you to r equal to 0. There is no escape. So for example, you can see this intermediate one. It is not that the particle can go into the horizon and then try to come out again. Once it is inside this event horizon, it cannot even stay at the same r. So in some sense, for an infalling material particle or an infalling photon, heading towards r equal to 0 is like us going from present to future. So the role of the radial and the time coordinates are switched, and going towards r equal to 0 is like going to future. So it is inevitable that anything which crosses the event horizon will end up at the singularity at the center. It is not that you can enter the horizon and somehow hang around somewhere in between or come out. So this is the idea of event horizon. And this particular formulation was published by Penrose in 1964. And Penrose gave the name trapped surface to event horizon. Of course, this analysis is for a black hole which is spherically symmetric and which is unchanging with time. So what Roger Penrose did was that, just a second, I seem to be missing a slide somehow. If you will give me a second, I will try to relocate it. Yeah, for some reason I have lost that particular slide, so I'll go back to this presentation. That was a very critical slide because it talks about the role of the famous Indian relativist Amal Rai Chaudhary from Presidency College. I think when the window had disappeared at that stage, I somehow lost one or two slides. So let me say that in words then. What Professor Rai Chaudhary did in 1953, he was a teacher at Ashutosh College in Calcutta. What he did was to write down the equations for a general case where you have matter without assuming any symmetry, without assuming that there is no rotation, and without assuming that there is no variation with time. And he gave a specific formulation which allowed us to track how the different aspects, rotation, shear, and overall density change with time. And it was obvious from his equations that in general, you will have formation of a singularity at center. So what Roger Penrose did was that he proved that once trapped surfaces form in any space-time, it is inevitable that a singularity will form. And he used topological constructs with the Rai-Chaudhary equation to prove this. So in some sense, the work of Professor Rai-Chaudhary was critical to what Penrose did in this, and he's getting the award for. By this time, this work was done in 1965. By this time, Roy Kerr had found a solution for a rotating black hole. This too had trapped surfaces, and he did not show whether formation of trapped surfaces, so Penrose did not show whether formation of trapped surfaces is inevitable in any collapse. So in that sense, the first statement, which is that if trapped surfaces form in any space-time, it is inevitable that a singularity will form. But it does not, we don't know whether in any given collapse, trapped surfaces will form. So that is part of what is called the cosmic censorship conjecture, which says that any singularity has to be surrounded by a trapped surface. This conjecture has neither been proven nor been disproven for normal kinds of matter. If you come up with exotic matter and situations, one can play around with it. But so far, there is no satisfactory proof or a counterexample that has come up. So this is basically what Roger Penrose did. He also did a lot of other things. He generalized the singularity theory to cosmological context with Stephen Hawking. So essentially, the formation of trapped surfaces leading to singularities for black hole is similar to the time reversed universe, which says that in past universe must have come out of a singularity. There is one work which I have not mentioned here, which is he showed that in case of rotating black holes, there are multiple event horizons. There is an intermediate region called ergosphere, and Penrose showed that it is possible to extract energy from a black hole by using pair production or decay of a particle in this ergosphere. This is called Penrose process. He also worked on what one would call impossible geometrical constructs. For example, you can see this Penrose triangle at the bottom. It's a representation of what you think might be there possible to construct in 3 dimensions, but it is not. It is similar to the kind of drawings which Escher used to make, and Penrose and Escher had nice collaboration over many years. Penrose also came up with the tiling for 5-fold symmetry. An example is shown at the right bottom over here. And such symmetries were discovered in quasi-crystals. And it was indeed surprising that when a Nobel Prize in chemistry was given for quasi-crystals and 5-fold symmetry, Roger Penrose was not awarded at that time. It would have been interesting if he had got that one as well. So now we transition to black hole in the center of the galaxy, in our galaxy. So the galaxy essentially refers to our own galaxy. Reinhard, Genzel, and Andrea, Ghez, they got the 1/2 of the Nobel Prize, divided half and half between them, for the discovery of a supermassive compact object at the center of our galaxy. So evidence for black holes in centers of galaxies had been around for several decades. And it was also known that the black hole mass is correlated with the mass of the bulge in spiral galaxies. So each spiral galaxy has a roundish object at the center that is called a bulge. And to give an example, this is a figure from a paper by Nadine and Rix, 2004, where the x-axis is the mass of the bulge in units of mass of the sun, and the y-axis is mass of the black hole found inside that bulge through indirect evidence. And you can see that these two are correlated. So therefore, it was expected that there should be a black hole at the center of our own galaxy. And Genzel started this particular work in early 1990s, and Andrea Ghez started this work in mid to late 1990s independently. They have used different instruments, different telescopes to do their work. So if you want to see the center of our own galaxy, how would you look? So this is an image of the galactic region. And there are several strips which you can see over here. Each one of them has been constructed in different wavelengths. And you can see that it is only in the near infrared, which is 4th from bottom, this one, that you can see the bulge reasonably clearly. And therefore, Genzel and Andrea Ghez decided to use this particular waveband for their observations. So the idea was to image the center of the galaxy, search for stars near the center, and use these observations, possibly velocities of these stars, to infer mass distribution near the center. Unfortunately, scattering due to dust causes significant reduction in flux. And even in the near infrared K band, which is what these people used, the reduction in flux is by a factor of 10 to the 3. So what you observe is only 1,000th of the emitted light. The other difficulty is due to the turbulent atmosphere. And because of this turbulent atmosphere, this is what we see as twinkling of starlight in the optical light. And if twinkling essentially is that this image of the star keeps on shifting on the sky by a small amount. Now, this is not good if you want to image a very crowded region in the sky where there are lots of stars, because they might even shift on to each other's positions and so on. So initially, Genzel used what is called speckle imaging, which is you use a very, very short exposure such that during that time, twinkling does not affect the position of the image. And then after you have taken all of these images, you use a few bright objects to reposition your frames and add them up and improve signal to noise ratio. So this is what they started with in early 1990s, and gradually they added other techniques, which I will outline shortly. The other techniques which they have used are adaptive optics and interferometry. Adaptive optics corrects the wavefront for atmospheric disturbance so that there is no twinkling, which of course means that you are actively tinkering with the wavefront as it goes through the telescope and into your camera. Now, once one can achieve this, this allows diffraction limited imaging from ground-based observatories, and that is fairly adequate for this purpose. So the use of adaptive optics led to detection of motion of stars near the center and determination of their orbits. Eventually, the teams moved to adaptive optics with larger telescopes and K-band interferometry. Andrea Ghez worked with the two Keck telescopes, and Genzel's group worked with the Very Large Telescope in Chile. They have now tracked stars in the innermost region over more than 2 decades, and there is clear evidence of a single unseen dominant mass at the center. So if we look at how the mass of the Milky Way interior to a radius r varies with r, you can see that the mass keeps on increasing as we go out and it keeps on decreasing as we go in. But this older determination kind of stops at 1 kiloparsec. Notice that this is log of r, which is plotted on the x-axis. So what these people did was to find out stars with the orbits which go very, very close to the center. I will show you some animations for this as well. And by combining the orbit estimates of the orbits, orbital parameters, figure out how much is the mass which is interior to the orbit of each given star. So about 10 years ago, they managed to get good observations of this particular star. Okay, and they found that if you can see clearly, this star has an orbital time period of 15 years, and about 10 years ago it completed one full orbit as observed by these people, and from there very good data was obtained. And then they found another star. Okay, so with these two, one knew that whatever is the extra mass, that has to be sitting in one particular place over here. If the mass interior to both these orbits is similar, that has to be sitting over here, and that puts a clearer constraint on what can be done. Recently, they have found another star which has an even shorter orbit, that is S62, shown in red over here. The observations are still sketchy, but they have already tracked it for more than one orbit. And in the next 5 or 6 years, they should have very good constraints coming out of this. So all of this gives you mass enclosed inside orbits. On the x-axis is distance from the center. It's a logarithmic scale. And on the y-axis is the enclosed mass. The expected event horizon is over here. Okay. The orbits of stars which I showed you, S stars are over here. S2, which was the second one which I showed you, and S62, which was the last one which I showed you, they have orbits going all the way in. So the radius of this orbit is only about 100 times, 200 times, or rather the same major axis for this one is only about 200 times larger than the event horizon radius. We do see things inside, but these are not stars. We see some X-rays. We see infrared flares every now and then there is a radio halo which is seen, which are even smaller. So in principle, it is possible to have an object, not a black hole, and still all the orbital data would be satisfied. But there are other galaxies where we have observations. For example, there is a galaxy where we have observed maser light from the innermost part of an accretion disk, which corresponds to roughly this scale, which is very, very close to the event horizon. Current status is that using S2 and S62, gravitational redshift has been measured for stars in the vicinity of the central object. Precession of orbit due to relativistic corrections has also been observed, and these verify the space-time geometry in the weak field limit. The K-band interferometry with 10-meter class telescopes has improved sensitivity, and results are likely to improve considerably in the next decade. So before I go to summary, I would like to show you a few videos. And I will also see if I can dig up the slide with Professor Rai Chaudhary's contribution. No, that seems to have completely disappeared in my copying process. My apologies for that. So this is from the Genzel's group. So you can see orbits of stars orbiting around the central part. Notice that this is a projection, which means there could be stars which are moving, but they are nowhere near the actual black hole at the center. This is a simulation of orbits around the central part. So it doesn't have the jitter which comes from combining observations. So now we are focusing in on the innermost one light month. There are still lots of stars which can be seen over here. One of the challenges in all of this work is that you don't really know the orientation of the orbit. You don't know the inclination of the orbit. So sitting far away, you have to work out all the orbital parameters, and it is not entirely straightforward. There are some very interesting non-trivial aspects to that. One of our BSMS students, one group, they had looked at it as part of their summer project and prepared an interesting report on that. So now we are down to one light day right in the middle. Yeah. Okay. So I'll just put up my summary slide and end. So the Nobel Prize 2020 for physics recognizes theoretical advancements and observational work that establish black holes as astrophysical objects. The citation somehow shies away from stating that Genzel and Ghez have established the presence of a black hole. Technically, they are correct. Roy Kerr and the EHC team perhaps have a stronger claim on that count, and maybe that will be the next astrophysics Nobel to be awarded. Thank you.
Thank you, Professor Jasjeet. This was indeed an insightful talk on 2020 Nobel Prize in Physics by Roger Penrose, Reinhard, Genzel, and Andrea Ghez on their work of black holes, the most enigmatic objects in the universe, as common people call out. So, with this, we will begin our interaction session. We have a couple of questions out there on Zoom and the YouTube. So, I now request Dr. Manav to take over and hold this session.
Thank you, Jasjeet, for this wonderful talk. Actually, we have received quite a lot of questions. And
Okay.
so just to mention that we cannot take all the questions one by one. Rather, we will club them thematically, okay, and then place in front of our speaker. So there are some attendees coming from Zoom, place some questions. So I will call upon Arindam Bhattacharya, AB. Can you please place your question, but please be concise and to the point. Arindam?
Yes, sir.
Yes.
Sir, my question is, I mean, if we can't see black hole, nothing is coming inside from it, then how can we recognize that this is black hole or something is there? How can we understand that there is something?
What we can say is the following. By looking at the orbits of stars, we know that there is some very massive object sitting in a very, very small region. Okay? So if you look at the slide over here, then that massive object has to be sitting in this tiny region over here. Correct?
Yes, sir.
Yeah? Yeah. So now let us go to this figure. So what it tells you is that the mass which is enclosed is around 4 million times the mass of the sun, and the size, radius over which it is distributed is, the units are 10 to the minus 4 parsecs. You can ignore that. What I can tell you is that this point over here would mark Earth's orbit around the sun. So something which is enclosed within 10 times the radius of Earth's orbit around the sun has mass which is about 4 million times that of the sun. So that is what has been established. Second thing which is established is not from these observations, but from observations of the X-ray hotspot, which is seen much further inside. So that is at a scale which is about a third of Earth's orbit around the sun. So we observe X-rays coming from that region. And the understanding is that these X-rays are coming from very hot gas, which is gradually sinking into the black hole. Okay, so that is the understanding that we have. Now, could you say that it is possible to have an object with a radius, let us say 2 or 3 times the expected event horizon, say, size, and it not be a black hole? The answer is that in principle, it is possible, but we don't know how to construct such an object from the physics that we know, or using astrophysical processes that we are aware of. So that is why the Nobel citation is also shying away from saying that they have found a black hole. They are saying that they have found a supermassive compact object at the center of the galaxy. But what we can say with confidence is that within a radius which is less than 10 times Earth's orbit around the sun, there is an object which has a mass which is 4 million times the mass of the sun. Does that answer your question? So we are not looking for something to come out of the black hole. We have to look for evidence from near the black hole.
Okay. Thank you, Arindam. Thank you, Jasjeet. So there are also a couple of questions came from someone called CBS Priyanka. Are you still there on the audience? Priyanka, can you please place your question in that case? If no, I will move to the next question. So there is another person named Prithviraj. Prithviraj, you placed a couple of questions too. Can you please switch on your mic and place the question?
Yes, sir. Good evening, sir. Thank you, sir.
No problem. Yeah, go ahead.
Basically, my question is that if light can't escape from black hole, it means that black hole is a sphere of energy from which light can't escape, and even though light is massless, but basically it happens due to time dilation. But what if a large amount of light energy gets concentrated at a point? Then will this energy concentration forms a black hole or something like that, sir?
Okay, so you are trying to envisage a situation where we focus a lot of photons in a very compact region.
Yes, exactly,
and
sir.
Then you are asking whether that will form a black hole or not.
Yes, sir.
Now, yeah. So, see, when you try to do that, you do have to contend with things like the uncertainty principle on whether you can actually focus things so well or not. But in principle, at least at a classical level, if you can get enough energy into a compact space, you can form a black hole.
Okay, sir.
So I'm glossing over the quantum mechanical complications, okay, which arise from the uncertainty principle.
Okay, sir. Thank you, sir.
Okay, so now I will move to the next question, but this time I will take a question from YouTube chat box, and actually there are quite a lot of questions. Again, I will not address individual question at a time. Rather, I will combine all of these in one question and place in on behalf of you. I will place in front of Jasjeet. So Jasjeet, one question came. For example, Emu, Surya, and some others also placed the similar kind of question. Is that what is the nature of space and time inside black hole? For example, if you talk about time dilation, or if there exists at all any space inside a black hole. This is the question.
Okay, difficult question, but at least for the Schwarzschild black hole, from what we understand, if there is a particle which is entering the event horizon, for that particle, decreasing r is equivalent to increasing time. Okay, So within a finite amount of time, it will reach the center. In order to do the kind of experiments which the person asking the question is thinking about, like time dilation, length contraction, etc., you have to do experiments and you have to be able to move around. That freedom is no longer there. Once you enter the event horizon, you are forced to r equal to 0, and that is a singular point, end of story. So one can map the structure. It is not that you cannot figure out what kind of the mathematical structure which is there, but for an observer to hang around trying to do that experiment, that is not going to be feasible. So let us say you are at a radius of half the event horizon radius. You cannot send a photon from that half the event horizon radius towards the event horizon. That is not possible. Any light which you emit will go towards r equal to 0 in finite time. So such constraints are there, but mathematically you can analyze the structure, and as long as you are not at r equal to 0, mathematically it is well behaved and can be understood.
Okay. Okay, so now I will move towards some question coming from Zoom audience. So Khushbu, are you there in the audience?
Yes.
If you are there, yeah. Can you please place your question?
Yes,
please
sir.
try to be concise and to the point.
Okay, sir. So my question is that if black hole is the end process of such large objects at very early in the universe, and like we have a large black hole at the center of our galaxy, so
Right.
how it formed so early?
I'm losing the audio in between.
Yeah. Khushbu, can you repeat once again?
The question? Yeah.
Yes, sir. So I was asking that if black hole is the end process of a star, and it is a very slow process, and we have a very large compact object at the center of our galaxy, so how this so early this happened?
Well, the universe is more than 13 billion years old. The more worrying observations are of black holes, which are like 10 to the 8 times the mass of the sun, at a stage when the universe was less than 2 billion years old. Okay, so such observations also exist. So clearly there have to be processes which are very rapid, and possibly processes which can, other than kind of endpoint of stellar evolution, which may be able to lead to formation of very massive black holes very quickly at some stage of the evolution of the universe. So there are some conjectures on how this may happen when the galaxies begin to form very early on, that there can be instabilities which can lead to very rapid inflow of gas, and without forming stars you may be able to form a big black hole. But these are still conjectures, and we have to work out the implications of these models, and then go look for observational verification before these can be adopted. The other picture, the more regular picture, is that black holes form from very massive stars, and these black holes merge and form bigger black holes. This process is something which has been observed using gravitational waves. So LIGO, Virgo observatories have by now observed tens of such black hole mergers, except that they have not, they cannot see mergers of very massive black holes. They can only go up to mergers of around 100 solar mass black holes or so. So we know that this process does happen. Theoretical estimates seem to be that this process of merger is rather slow, and therefore this may not be the only thing. There are other things which we may be missing. This is something which is to be worked out with more observations and better theories.
Okay, sir. Thank you.
It is an open question. Yeah.
Okay, so now I will go for the next question coming from Jui Kundu from our Zoom audience. Can you please pick up, Jui? Are you there in the audience? Okay, if no, I will go to Mohan Krishnan. Yeah, Krishna.
Sir, good evening.
Yes.
I'm here.
Place your question.
Sir, really this lecture is quite innovative. Then it's really our thinking is a little bit higher. My question is very clear. Is any proportionate is there for real object and black body? That is the first question. And second thing, what is the role of forming a black hole in gravity? What is the role of a gravity in forming a black hole? That's the two questions. Am I clear, sir?
No, can you repeat the first question? That was not very clear to me.
What is the proportionate between the real object and black hole? That is planet and black hole.
Oh, okay, okay. I understand.
Is there any relation? And second question is, what is the gravity role in the formation of black hole? That is the two questions.
All right. So I'll answer the second question first.
Yes.
Essentially, when you have any stable object like a chair or a table, there are some forces which are preventing it from collapsing. In case of a chair or a table, these are solid state forces between adjacent atoms which hold the thing up. When you go to larger objects like the earth, there are still mechanical forces, pressure, which is holding the earth, and it is preventing it from collapsing. You go to the sun, there is pressure from gas pressure as well as radiation pressure, radiation which is coming from inside the sun, which is preventing it from collapsing. Okay. So if you have a star in which energy generation suddenly stops, okay, as happens when a star reaches the end point of its active life, it runs out of fuel at the center. Since there is no energy being generated, suddenly there is no pressure. If there is no pressure, there is nothing to balance gravitational force, and therefore gravity essentially overcomes everything, and it leads to formation of a compact object.
Okay.
Now, if the mass which is collapsing is less than Chandrasekhar mass limit, then you probably end up in a white dwarf star.
Yes.
If the mass is a bit more or whereabouts, you may end up in a neutron star. If it is much more, then you will end up in a black hole. That is our understanding. But in each case, for stable objects, gravity is being balanced by something. If that something which is doing the balancing disappears, as it does when stars reach the end point of their life, then collapse can happen and black holes can form.
Thank you. Thank you.
Going back to your first question in terms of how many black holes are there and how many stars are there. So in our galaxy, we believe that there are about 100 billion stars, 10 to the 11 stars in our own galaxy. There is no easy way to count the number of black holes, but most estimates give you numbers which are of the order of 1,000 or so.
Okay.
Okay, so it is very, very small in number.
Yeah.
Okay, so now I will go towards a couple of questions coming from YouTube chat box. So one question came and it says that we know that from black hole nothing can escape, but we also get to see that there are some jet of mass coming out of black hole. So are not they contradicting, means or something is missing here in understanding?
Yeah. So the understanding is that we have a disk of material which is gradually falling towards a black hole. This disk of material heats up, so it essentially becomes very hot plasma. In this plasma, one has magnetic fields, and it is believed that in the inner parts, not inside the black hole, still outside the black hole, in the inner parts, the magnetic field structure is such that it can channel material which begins to fall towards the black hole into a jet. Okay, so there are mechanisms which have been thought of in that context. Again, not entirely tested for the simple reason that it is not easy to test such things. We can only observe. We cannot recreate such a situation. So the jets are forming outside the black hole, but they are forming fairly close to the black hole. As you have seen in case of our own galaxy, the radius of the black hole is of the order of a few times larger than, or the radius of the event horizon is larger than the radius of the sun, but it is much smaller than the radius of Earth's orbit around the sun. Now, this is extremely tiny to compare with the size of the bulge of our galaxy. So the central black hole sits at the center of that bulge. We are talking about a difference in scale of a factor of 10 to the 8. Okay? So the bulge is 10 to the 8 times bigger than the black hole. So therefore, it may seem to be coming from the black hole, but it is not. It is just coming from somewhere very, very close to the black hole.
Okay, so the second question from YouTube is like this. So it says that what happens if two black holes collide? And so this is the first question. Second question is that also we got to know from our gravitational wave experiment observation that two black holes, when they collide, they can create gravitational wave. How come this wave even can escape from this black hole? So this is the second question.
So the wave is not escaping from inside the black hole. When two black holes are proceeding towards merging with each other, the space-time around them is highly disturbed. And because they are in orbit around each other, this disturbance is somewhat periodic. It is this periodic disturbance that we are observing as gravitational wave. So gravitational wave is not something which is kind of originating inside a black hole and then coming out. And when two
about
black
the
holes,
first question?
Yeah, when two black holes collide, the space-time structure gets disturbed and gravitational waves are emitted. They are emitted in two parts. One is the process leading up to formation of a black hole. And that has the famous chirp waveform. And people have worked out what kind of a waveform to expect for different types of merging black holes. The other component of gravitational wave emission is that when a black hole forms, at that stage, it is not, the event horizon is not spherically symmetric. So it has to lose its asymmetry and settle down to either a simple rotating black hole or a spherically symmetric black hole. And in order to shed all these excited modes which are there, it emits gravitational waves in what are called quasi-normal modes. These quasi-normal modes were worked out by C.V. Vishweshwara, an Indian general relativist who used to call himself a black holy man. He worked out these things back in 1970s, and he demonstrated that the spectrum of gravity waves emitted in quasi-normal modes depends only on the mass of the black hole for a Schwarzschild black hole, which means that if you could observe the spectrum, then you will know that you have observed a black hole of this particular mass.
Okay.
So I would just would like to take a couple of seconds because I think it is important. People should know what Professor Amal Rai Chaudhary looked like. This is his picture. I hope you can see it. And he was a doyen of Indian relativity. He did a lot of very original work, worked in a college, and he always took a lot of interest in teaching students. I'm sure there are a number of people, even within the society, who would have personal recollections of him or have recollections through his students. Penrose's work was founded on Rai Chaudhary equation, so it is very important to honor him and his work and his memory when we are talking about Penrose's work. Yeah, Manav, please go on.
Yes. So now we have time for maximum 2 questions. So I will take one from the Zoom audience and another from YouTube chat box. So Vijay, are you in the audience? Can you please place your question directly to the speaker?
Yes, sir. Am I audible?
Yes, go ahead.
Yes.
Thank you. Good evening, sir. Sir, my question is, through whatever the evidence we have right now, how much theories about the black hole and singularity we can accept? And I have another question, that can we connect the theory of Big Bang with the theory of black hole anyway? That's all. Thank you.
Okay, so again, second question first. The connection is there in the sense that What Penrose did was to say that you have formation of a trapped surface, and when you have formation of a trapped surface, after that formation of a singularity is inevitable. Stephen Hawking did this, essentially considered the universe to be a time reversed picture of a collapsing black hole, except that the universe at large scales is known to be homogeneous and isotropic. So one does not have to worry about rotation, and one does not have to worry so much about shear. So Stephen Hawking did connect it at that level. But other than that, there is no connection that I am aware of. The first question was, how much can we trust the theories of black holes? Well, there are two steps to it. One is that we have by now verified Einstein's theory of gravity in a wide variety of situations. And it has always come through. It has passed the test with flying colors, always. So therefore, any prediction of the theory has to be taken very, very seriously. And the Event Horizon Telescope, the work being done by Genzel and Andrea Ghez, and also work being done by many radio astronomers who are probing the inner regions of galaxies around black holes and measuring black hole masses. All of that implicitly assumes that Einstein's models are valid, and that is what they are using for doing all the calculations. And it seems to be coming through as far as we can tell so far. So the proof of the pudding lies in eating, and the proof of any scientific theory is in being consistent with observations and with experiments. In this case, we cannot do experiments, but we can certainly carry out observations. Einstein's theory is also tested in an indirect way when people do experiments on equivalence principle, because equivalence principle, which is the proportionality of the inertial mass and the gravitational mass, is a foundation stone of Einstein's theory of relativity. And this has now been tested over length scales, which differ by a factor of about 10 to the 20. So it is absolutely remarkable that it has come through. And for any theory which has been so successful, we always take any implications, any predictions very, very seriously. And one reason for taking them seriously is if one of the predictions turns out to be wrong, then you would have found out exactly where Einstein's relativity breaks and search for the alternative restart. So you keep on pushing the limits until you find a breaking point. So far, we haven't.
Thank you, Jasjeet. Actually, the last question that I want to place also in relation to the discussion you made, and that is, what are the failures of general theory of relativity so far? Actually, this is one of the questions also came from YouTube.
Yeah, in terms of observations, none that we know of when you take error bars into account. There has been an experiment called Gravity Probe, which looked at dragging of inertial frames, which has been predicted by Einstein's theory. And this experiment worked with gyroscopes in satellites around the Earth. They found something which was slightly off from Einstein's theory of relativity, but their error bars were so big that within 2 sigma, Einstein's theory is consistent with that particular data. One hopes that people will be able to improve on that experiment. Other than that, I am not aware of anything where Einstein's theory doesn't fit in much better than this one.
Okay, thank you. So there are actually quite a lot of questions. Many of them are general, some are technical, but unfortunately we are running out of time and we will not be able to accept all these questions in this session. But you can certainly...
questions can be put together and emailed to me. I will try to answer at least some kind of offbeat ones. Yeah.
Okay, so this is one of the things we have to see how we can, because the questions are coming from different person. That means they're individually if we have to address. But otherwise, if you pose your question on YouTube, there we can place the answer. Okay, YouTube chat box. Yeah. So thank you, Jasjeet, for this this interactive session. So with this, I will hand over the program to Deepti. So over to you, Deepti. Thank you.
Thank you, Manav. We've come to the end of the session now, and I now request Professor Soumitra Banerjee to give the vote of thanks. Professor Soumitra Banerjee is a professor with Department of Physics, IISER, Calcutta, and also the General Secretary of Breakthrough Science Society. Over to you, Professor Soumitra Banerjee.
Thank you, Deepti. It is really a pleasure to listen to Jasjeet, because he has been in the forefront of the field, and he has exposed to us different aspects of the discovery that led to the Nobel Prize this year. But as you have probably heard, this time the interest that was generated was quite large. The number of registrations was more than 4,000. And it is naturally expected that not all the 4,000 would be physicists. So people from different backgrounds would be there. And since Breakthrough Science Society looks at propagating a scientific temper, a scientific bent of mind, it is all the more necessary for people to understand how science works. Even though we may or may not understand the nitty-gritty details of a scientific discovery, we should be able to understand how a scientist's mind works. And his talk has made it clear that a scientist, their theories, their beliefs always have to be tested by observations, by experiments, in case of astronomical things, by observations. And he has quite elaborately illustrated how the theories have been established through very meticulous observation. And there is a lot to learn from that. For the common people, those who are not inside science for that matter, it is interesting to note from his talk that how big the universe is, how big our own galaxy is. And in that context, our solar system, the Earth, is just a speck of dust. And if you look at it from that point of view, the small problems of religious, political, ethnic, all these problems become insignificant when you look at the whole tapestry of the universe. So this has been very clear from his talk. And for the science students, it is necessary to understand, for everybody is necessary to understand, this whole universe works on the basis of laws. It's a law-governed universe. And for science students, it's necessary to understand what the laws are. And he has quite nicely illustrated the discovery of the general relativity, the gravitation, our understanding of gravitation. And that is the law that sort of explains the behavior of the whole universe. I would like to thank him with the core of my heart for this wonderful talk that elaborated various things and made things clear to the people who didn't know the details of this discovery. I would hope that we will be in touch. We have been in touch because he is the Dean of Academic Affairs in one institute, I am of another. So we are in touch. But apart from the academic contact, also in terms of getting science to the people, the motto of the Breakthrough Science Society, I hope that we'll be in contact from that aspect. Thank you, Jasjeet. Let's finish.
Thank you, Soumitra. Thank you.
Thank you, Professor Banerjee. And thank you, Jasjeet sir, for an insightful talk. I'm sure most of us are going to watch it again and again for understanding. And indeed, it was a wonderful Sunday for most of us in listening to a lecture like this. Let's all stay in touch. Let's all be safe. Of course, we're all in COVID times. You will expect more and more lectures from us, and we will be ready. So let's all get up for that and have a wonderful evening. We request all of you to fill in the feedback form that's out there in the chat box, and that's how we'll know what else you all want to know. So thank you, everybody, and have a wonderful